Hello, and welcome to Lecture 19, Part 1 of Life in the Universe. In this lecture, which I think we're doing in two videos, we're going to do Unit H, which is about the formation of planetary systems. The first video of the lecture, however, we always have an alien to look at. And here is our first representation for the semester from the Star Wars universe, seen from Return of the Jedi with Jabba the Hutt and some of his minions. Now, you may have noticed I've had a lot of Star Trek universe references. This is the first Star Wars. There will be another Star Wars, but I do have a lot more Star Trek and Star Wars references in it. And that is because in Star Wars, the aliens really aren't, for the most part, depicted as being uh, uh, thinking in terms of what alien life might plausibly be like. They're basically just funny looking people. And the most egregious example of that is in Attack of the Clones, where Obi-Wan has a friend who's running a diner on Coruscant, and except for the fact that he's got four arms and he's green, the same character with no other changes could plausibly be running a diner in New Jersey. And I don't think that somebody running a diner in New Jersey is a likely person you'd find on the capital planet of a galaxy spanning civilization a long time ago, far, far away. But be that as it may, I guess I'll just mention, one thing about Jabba, since he is one of the more alien-looking aliens they had in Star Wars, kind of slug-like, but with a distorted but human-like face and human-like forearms. Um, uh, and I guess the original Jabba was originally all animatronics. They had some CGI ones that they put in at other places later. I think this little critter right here was a Muppet. Anyway, we'll have more Star Wars in before the semester's out. And anyway, I just noticed I will have the links if you want to go listen to some of the soundtrack by John Williams. You can. One thing that summer before last got to see the original Star Wars movie shown at Tanglewood with the Boston Pops uh, playing the soundtrack live, playing the score live. That was pretty cool. And John Williams is pretty old now. He doesn't really conduct much anymore, but he was there, so that was pretty cool. And was going to see The Empire Strikes Back this last summer, but for reasons of which I'm sure you're all too aware, the Tanglewood summer season was canceled this year. All right, so our topic here is to uh, take a look at our understanding of the formation of planetary systems. And maybe as a motivating picture, here's the Hubble Space Telescope image of a disk of material around a young star uh, in front of the Orion Nebula. So the disk itself is fairly absorbing of light, but then the nebula behind it provides a nice silhouetted view of it. The image on the left is the raw image, and the one on the right has been processed to bring out more of the fine detail. And if you notice the date on this, 1995, this would have been about the time we were starting to discover exoplanets. But even before that, it is identified as a protoplanetary disk. And if you recall that uh, the planets all orbit the sun in the same plane, and most of the stuff goes around the sun in about the same plane. Uh, Even before we started finding other planets, it had been hypothesized that something like this is where planets might form, and the fact that these are fairly common around young stars is a very encouraging sign. All right, but maybe a little bit more of the history of this, and it's a much more complicated history than we have time to get into very much. But the basic idea of how we think planetary systems form today is a modern version of the nebular theory, or nebula hypothesis might be better, because It would only be some specific version of it that would have the detail of a theory. And anyway, the basic idea is goes back quite a while. In fact, it goes back before the time of Newton. The first person we know of that described something like this in a qualitative fashion, which means didn't try and do any calculations as to how it might work, but just kind of did a plausibility argument as to how it might work, was the French philosopher Rene Descartes, who sometime, I think, been before 1650 when he died, but I think it wasn't published until after he died. Emanuel Swedenborg, also yeah, after Newton, but in a non-Newtonian aspect, described kind of a similar idea. Swedenborg was kind of an interesting person. I probably should learn more about him. Sorry, I hit the microphone there. Early part of his adult working career, he made some important contributions to science, including this. And then he started having visions, visions where angels would take him to Saturn and show him various wonders there. And for the rest of his life, he largely wrote he wrote a lot of very interesting and kind of odd theology. And I guess as evidence that angels weren't really taking him to Saturn, as our spacecraft has since gone to Saturn, don't see what he said he saw. I suspect he wasn't really going there. But in any event, the first person to describe the idea in a Newtonian framework, so thinking in terms of Newton's description of gravity, again, still qualitative, was the German philosopher Immanuel Kant, who wrote a book in 1755. It was quite a substantial contribution to astronomy at the time. We'll talk about it a little more. No, let's see, in this course, my ASTR 101 class would come up again. I don't think it will in this one. Uh, but then the first person to do a quantitative version, to actually sit down and try and do mathematical calculations of how this physically might actually work in Newtonian gravity, was the French mathematician Pierre-Simon de Laplace in the 1790s. Anyway, the modern version, obviously, as we're going to see a little bit, is very different from, we're not looking at all the details, but the modern version will be very different from what Kant and Laplace were thinking about over 200 years ago. But the basic idea is still the same, that you form the entire solar system, sun, planets, everything else, from the same cloud of interstellar gas. And we'll talk, when we get to talking about stellar evolution, we'll talk about star formation. We'll look at this from the point of view of the stars. But if such an interstellar cloud of gas starts to collapse under its own gravity, and if it has a little bit of rotation, which is what it means to have angular momentum, there's a principle called the conservation of angular momentum that means that instead of it all collapsing into a single object, it'll collapse such that you have a concentration of matter in the center with a rotating gaseous disk around it. We call this gaseous disk, if we're talking about the solar system in particular, the solar nebula. If we are talking about this in general, it could be just a protoplanetary nebula. And before the concentrations of the center actually becomes a star, if it's specifically the sun, we'd call it the protosun in that stage. A protostar would be the more general term. And then if you form the planets in that disk, then right away you take care of two of the features of the solar system we have to explain. Why things orbit the sun in about the same direction and in about the same plane. That just naturally comes out of that. Now, this idea was pretty popular until the late 1800s, at least the Laplace's version and kind of what had developed out of that after a few decades. But in the late 1800s, it kind of fell out of favor because there were some problems given what they knew at the time. They had trouble understanding how to solve. And then, so throughout the 20th, first half to 2/3 of the 20th century, there were a number of alternatives that were proposed. One of which, in 1905, Thomas Crowder Chamberlain was a geologist. Forrest Ray Moulton was an astronomer. And they proposed an idea that was heavily favored for 20 or 30 years. And they proposed that perhaps another star, the sun had formed separately from the planets that already had existed, but then another star happened to pass very close to the sun, and the gravitational pull of that other star pulled some of the material out of the sun, some of which ended up in orbit around the sun. And then solid particles then condensed uh, from that gas. We'll say a little bit more about that in a moment. And then those little solid particles, by colliding and sticking together, you basically build up the planets by accretion. And the term planetesimal is something they proposed as to what to call these growing bits of things once they get to a certain size. And so the term planetesimal has been taken over into the modern theory, as well as the idea of condensing the stuff out of gas, but being added into the modern version of the nebular theory. And I'll say a little bit more about that in a second. But first, this is actually a great time to do our secret code because it involves Chamberlain. And remember, don't email me the codes anymore. You need to go take the quiz on Plato about this video. And one of the questions will be about the code, but the others will be about the other content. So the code here is Herbert McCoy's book. And by this, I don't mean a book written by McCoy. It was a book McCoy owned. So McCoy was a chemist who was at the University of Chicago when Chamberlain wrote this book in 1916 about this idea of the formation of the Earth and the planets. Chamberlain was chair of the geology department at Chicago at the time. And this is a particular copy of that book that he gave to McCoy. And the reason I know about that is here's the book right here. So you can see right here, it's from the library of Herbert and McCoy. And the writing you can see there in Chamberlain's handwriting, and I confirmed that, is that it's to Professor McCoy from Chamberlain. So Chamberlain would have actually have handed this book to McCoy. And one thing that's kind of interesting about that, if you read the preface, I'll see if you can see it, that I don't know if it's going to be legible here, but here he thanks people who ran the manuscript. Moulton, of course, is astronomical collaborator, McCoy, and then the R.T. Chamberlain was another geologist who was this Chamberlain's son, but was also, by the time this was written, was an adult geologist. So kind of a cool little bit of this history to have. All right, back to the share. I'm going to have something to show you before this video is over. I hope that will be much more interesting from a very deep historical aspect. Now, so the question is, how do you actually get these solid particles to condense from a gaseous state? Well, let's see here. If I turn this up towards the sky, I don't know if you can see anything, but unfortunately, probably doesn't show up very well. But the clouds that I ordered as a demonstration here are not visible. They didn't show up in time. You have to talk to complain about that. But let's think about how clouds form in our atmosphere. I'm sure you know that clouds in our atmosphere are made of water. They are not, however, made of water vapor, water in a gaseous form. Water vapor is invisible. You can't see it. And I'm sure you've all noticed you can see clouds. Instead, clouds in our atmosphere are composed of either little droplets, tiny little droplets of liquid water, or little tiny ice crystals. That's actually more common, especially in the winter. They're all going to be ice crystals. Some of the lower ones might be liquid water in the summer. But anyway, these little liquid droplets or these little ice crystals are light enough where they can remain suspended in the atmosphere unless they grow too big, in which case then they fall as precipitation. The point is that if you've got the right temperature and pressure conditions in a gas, then some component of that gas, and it could be a trace constituent like water vapor is no more than a couple percent in our atmosphere, that a trace constituent, sometimes a major constituent, but often a trace constituent, the right temperature and pressure conditions, that component will condense from a gaseous state to either a liquid or a solid state. And I'd imagine if you've ever flown before when it's cloudy, presumably in an airplane, maybe you just flapped your arms really hard. But if you're in an airplane, you probably noticed that unless there is a lot of convection to mix the atmosphere vertically, that the cloud layers tend to be pretty well limited in altitude. And that's because, at least at the altitudes where planes fly, the temperature decreases as you go up from the surface. The pressure certainly decreases. So the clouds are at that elevation where the pressure and temperature is right for the water vapor to be condensing. All right. So, anyway, once you get these originally microscopic particles condensing, then occasionally they're going to collide. And when they collide, sometimes they'll stick together and they're going to have a tendency to grow with time. And once you get them up to sizes of a kilometer or so across, then they're by that point they're massive enough for gravity to accelerate the growth. They'll grow faster, and the idea is you then build up the planets from the accretion of many, many of these smaller pieces. And by the way, it's when they get to a size about a kilometer that we would start calling them planetesimals. So here's kind of a cartoon view of it with temperatures on a, I mean, not temperature sizes on a logarithmic scale of some sort. So we start with really, really tiny particles, microscopic, really microscopic, maybe at about a nanometer size, that we would probably call dust. And at some point, you grow up at some time, maybe above a millimeter up to a few meters, we'd call them boulders by the time you got that big. And then, like I said, from the kilometer size up to maybe 10 to 100 kilometers, you call them planetesimals. And then once you get things maybe up to around 1,000 kilometers or so, they're big enough, you call them a planetary embryo or thereabouts. Now, another thing we've got to explain about the solar system is why you have terrestrial planets close to the sun, Jovian planets, and icy things further from the sun. Not an official term, but I think cryoterrestrial, cryo means cold, might be a good name for the icy things out there. But anyway, the thing is, the protostar, protosun, if it's going to be the solar system, even before the nuclear reactions start in the core, is still going to be pretty warm because of the conversion of gravitational potential to energy as into heat as it contracts. And so it's going to be pretty hot near the sun or the protosun, protostar, if it's not our system. And the only thing that can condense there are things that can be solid at fairly warm temperatures. So that basically means metal and rock, which is made out of relatively rare components of this gaseous disk, which remember is mostly hydrogen and helium. Actually, you don't have to remember that because can't remember that because I probably just told you that for the first time. It's mostly hydrogen and helium. So that means there's relatively little material for the terrestrial planets to work with, which explains why they're not all that big, and also why they're composed of metal and rock. If you get far enough out past something that we might call the snow line, it's cold enough for ices to condense. And by far the most important of the ices in this case, is going to be water ice for two reasons. One, water ice will be solid at temperatures warmer than any of the other ices that we considered. And think about what water is made of: hydrogen, the most common element in the universe; oxygen, the third most common element in the universe. So once you're out far enough to get water ice condensing, if you're outside the snow line, then you have a lot more material to work with. So that means the Jovian planets can actually grow faster and much bigger. They actually get to be massive enough where they can gravitationally capture hydrogen and helium gas directly from the nebula. Probably never be cold enough in the outskirts for hydrogen or certainly helium to condense. And so it explains why the Jovian planets are so massive. And it also explains why the smaller things in that part of the solar system have substantial amounts of ice because that material was available. All right. Now, it turns out we actually have a couple of different ways that we might form a Jovian planet. And so I probably mentioned that. So the core accretion model is what I just described. So the idea is you start by accreting a lot of planetesimals, presumably a mix of rocky and ice ones. And once that gets to be big enough, you get gravitational capture of the atmosphere. And the structure it gives you is in a Jovian planet. Might be mostly atmosphere, but it would have a icy, rocky with some metal core. Another possibility is that you could have these planets forming kind of like stars in miniature, as by gravitational collapse directly of gas. And if you did that, you'd think it would be great because then you'd get a planet without a core. And any of the heavier, material that would be ice or rock otherwise would be more evenly mixed. So it seems like you'd have a way of determining how an individual Jovian planet formed based on whether or not it has a core or not. The problem is, although you can go this way to end up with a planet with a core, after you could form a planet without a core and then have that denser, icy, and rocky stuff then differentiate and sink to the center to produce one with a core. Also, it's plausible that you could form one with a core, and then the core could then dissolve into the surrounding hydrogen helium envelope. So it seems there are multiple channels to get to either end state. Anyway, but I'd say the general consensus is that probably most Jovian planets still form by core accretion, but others might form from this disk instability and that disk of gas leading to gravitational collapse. And unfortunately, for an old planet like Jupiter, observation of whether or not it has a core or not won't necessarily tell you which mechanism was responsible for its formation. All right, so this is kind of a cartoon view with time. Let's see if I can write time. Yeah, well, almost legible, right? Time increases from top to bottom, and maybe someday I'll learn how to do a straight line with any of these. Okay, but anyway, up at the top here, we've got our interstellar gas cloud slowly rotating that starts to collapse under its own gravity. Conservation of momentum causes it to flatten into a rotating gaseous disk with a protostar at the center. You start condensing material from that disk on the inner part of it, and this is not to scale, by the way. The inner part of it in here, inside the snow line, it's too hot for anything other than metal or rock to act as seed for planet growth. Okay, outside the snow line, it's colder. You can get ice. So you have different materials and a lot more material to seed planet growth. Oops, skipped ahead here. So down here, we've starting to build up accrete the planets together. And then one thing we haven't talked about yet, but young stars tend to have very powerful stellar winds. And once those get going, that'll flush out most of the gas and dust that hadn't already been incorporated into something bigger. Now, the evidence that these kinds of disks from which we think planets form are common around young stars and pre-stars is very good, and then particularly the ALMA interferometer working in kind of the far infrared submillimeter region is particularly good at observing them. And so here is one where he actually is resolving some structure in it. So the protostar itself is where I just put the really tiny little dot there. But you can see that there are gaps in the ring. There's at least one, two, three, maybe four, maybe five gaps, maybe even a sixth one out there in that ring. And one thing are the computer models of how this would work, what it predicts, is that the forming planets would clear out these gaps as they're sweeping up material in there. So even though you couldn't see the planets individually at themselves in this, we may be seeing their effects as they are sweeping up the material in the regions where those gaps are. Now, the small solar system bodies, the comets, asteroids, Kuiper Belt stuff, and so forth. One way to think about those is those are basically the leftover planetesimals that have not, or perhaps many cases, have not yet been incorporated into planets. And this gives us a way to study some pretty pristine material because meteorites are basically just very small asteroids that have survived colliding with the Earth. Something that's really small will just be vaporized when it hits the atmosphere. Something depends on the composition, but something from maybe about the size of a pea up to a few meters in diameter will be slowed down by the atmosphere to the point where it doesn't all vaporize and it will hit the ground maybe 100, 200 miles per hour. You wouldn't want to be hit by one, but it wouldn't cause much damage, and they're in pretty good shape when they get to the ground. And anyway, some meteorites, if you look at the details of the structure, they show they have not been significantly modified since, or at least not completely modified since the solids of which they're made would have condensed in the solar nebula. And in particular, a type of meteorite called chondrites are kind of ideal for this. They're called chondrites because of these round structures in them called chondrules. So this is a little piece of a chondrite meteorite that's been sliced thin so you can kind of see the structure. So these round things here are the chondrules, and the chondrules themselves have been melted. So they're probably little free-floating blobs of molten rock at some point in early solar system formation, and surface tension would hold a little drop of something liquid even in vacuum together. But it's the material in between the um, the chondrules called the matrix. That if you look at that, that has never been melted. So whatever of the object this meteorite was originally part of, whatever assembly it did, it never got big enough and hot enough to melt it all the way through, as we'll see about. And I should also point out that a small amount of these meteorites, it's about 1/10%, consists of these microscopic size little bits of solid that are apparently predate the solar system. So these would be little bits of interstellar dust from the interstellar gas cloud that formed the solar system that were not at any point melted or vaporized in the process of forming the solar system. And let's see, I think, yeah, that's my last slide. So I'm going to get out of the share here. So that meteorite that I was just showing you, this is it. And in fact, this isn't going to be as good a picture of it as what you were seeing there, especially because I'm not going to take it out of the case here. Keep my oils and stuff from my finger off of it. Let me see. But you can see the chondrules in there, and then the matrix in between would be most stuff that condensed in the solar nebula as the solar system was forming, but very little has happened to it. It's had no significant modification in the last 4.56 billion years. So this little piece of rock is 4.56 billion years old, except for the pre-stellar dust grains in it. So about 6 milligrams in this piece of this meteorite is older than the solar system. You have actual solid things that existed before the solar system did. And incidentally, interstellar dust apparently forms in the atmospheres of red giant stars. And who knows? Some of the stuff in there. There might be a piece or two there that might even be 10 billion years old. All right. Well, that's it for this video. I think I just have one more for this lecture, but I'll know for sure when I go to do the next one. So let me go do what I have to do before I do that one.